Okay, ladies and gentlemen, welcome to today's lecture on EEC 393 Digital Signal Processing. Today, let us start and study about the properties of DFT, which is the discrete Fourier transform. Okay, there are numerous properties. Many are similar to that we have studied before. Some are peculiar to DFT. So we shall try and concentrate on the peculiar property rather than the generic properties which we have been studying all along. So, naming the properties, first of all, there is linearity. Then there is periodicity, followed by we have the circular time shift, and then consequently the circular frequency shift, then again we have the time reversal property, followed by our circular convolution, the symmetry property, and last but not the least, the Parseval's theorem. So, as you can see, there are many properties which are quite generic to all the previous transforms, and there are quite a number of few peculiar properties such as the circular time shift, frequency shift, the circular convolution properties. So our task is, or rather I should say, we shall concentrate mainly upon the peculiar properties and show proof of those properties only. I hope you can easily prove using the direct transformation for linearity, Parseval's theorem, and such properties. So let us proceed with our first property, the periodicity property. So periodicity. So in this property, it states that if x of n, which is any discrete time domain signal, has a direct DFT transform, that is x of k, then as for the periodicity property, for all n which goes from 0 to n minus 1, note that n being the length of the sequence x of n, capital N be the length of the sequence of the signal x of n, then the signal x of n will be periodic, which can be given by x of n is equal to x of n plus n. That means the x of nth sample will be equal to the x of n plus nth sample. And same goes for that in the frequency domain, n which goes from 0, k which goes from 0 to n minus 1, x of k will be equal to x of k plus n. So as shown before, this is the basic condition of periodicity. So what I'm trying to say is that if a time domain signal, a time domain discrete signal is periodic, then as per the DFT, the DFT transformation will also be periodic. So we know from the equation of the direct transform, x of k will be equal to summation, where n goes from 0 to capital N minus 1, x of n e to the power minus j twice by kn over capital N. Now then, x of k plus n will be equal to summation, where n goes from 0 to n minus 1, x of n e to the power minus j twice by replacing this k with k plus n, small n over capital N. Now decomposing this exponent term into two parts, we get summation, where n goes from 0 to capital N minus 1, x of n e to the power minus j twice by kn over n times e to the power minus j twice by capital N, small n over capital N. So this capital N and capital N will cancel each other out, and we will get summation, where n goes from 0 to capital N minus 1, x of n e to the power minus j twice by kn over n times e to the power minus j twice by n. Now this expression we have seen many a times earlier, where we have shown that any exponent in the form of e to the power minus j twice by theta will always be equal to 1. This value will always be equal to 1, and if you want to verify it, just expand this using the Euler's relation, and you can plug in the values of cos and sine, and you will get 1. So on that note, this expression will also become 1. So if this becomes 1, all we are left with is summation, where n goes from 0 to capital N minus 1, x of n e to the power minus j twice by kn over n, which is nothing but this expression over here. So this can be simply written as x of k, and hence equating the left hand side to the right hand side, we get x of k plus n will be equal to x of n. Hence it is enough to prove that if a signal is periodic in the time domain, in case of discrete Fourier transform, it shall also be periodic in the frequency domain. So this was our periodicity property. Now let us move on to the next properties. Okay, now before going into the circular shifting properties, that is the circular time shift property and the circular frequency shift property, first we must acquaint ourselves with what is circular shifting. So let us say circular shift. Now considering a sequence of length n being x of n, so any signal x of n which is having a length n, where n is the length or otherwise total number of samples, and obviously small n will go from 0 to n minus 1. As we have shown earlier, we must limit our range of vision from 0 to n minus 1 in case of our discrete Fourier transform. So now for any integer n naught, say x1 of n is equal to x of n minus n naught, where x1 essentially means that the signal x of n being shifted by a value of n naught, to be specific, delayed by a value of n naught. So graphically speaking, if this is our signal, so this is the n axis, this is x of n, the signal being something like this. So here is a value in the 0th sample, similarly the first, second, third, fourth, and this will be the n minus 1th sample. This is the 0th sample. And now for the ease of calculation, say n equals to 6. So just say this is a value I have taken arbitrarily. So n minus 1 will be equal to 5, and making this our 5th sample. Now then, if n naught is equal to 2, this is also assumed. So in case of our linear shifting, which I have shown over here, the signal will look something like this. So since there is a negative sign, the signal will be delayed from the previous position. So it will start, this is the first, second, 2 samples later. So this is first sample, this is one delay, this is another delay, and the signal will go over here. So if this is 0, this is 1, 2, 3, 4, 5, 6, this will be 7. This is n, and this is x of n minus n naught. Now then, if we do so, as for the more perceptive of you, there arises a discrepancy. And what is that? In our case, n minus 1 was 5. But if we shift the signal if we shift the signal by n naught, what happens is that the signal goes out of the range of 0 to n minus 1, which is 5 in our case, and the new signal ranges from 0 to 7. So what I mean to say is that we have violated the law that we should limit our range of vision from 0 to n minus 1. Hence, for that reason, the linear shifting, the linear time shift or frequency shift is not applicable for the DFT signals. And for that very reason, we must resort to the circular shift. The circular shift being that the signal will shift following the points along the radius, along the circumference of a circle. It will be much more clearer once I show some examples. But before going into that, why are we shifting along the circumference of a circle? So if this is the direction of our shifting in the anti-clockwise direction, one must observe quite carefully and quite promptly that if this is the first sample, say we have shifted for 4 times, then the signal will repeat back to the initial position. I hope you understand that. So this is the first sample. If we shift for value of 1, the first sample will go over here. Then for the value of 2, the sample will shift here. Then it will shift here. And for the fourth time shifting, it will revert back to its initial position. Now, why is that? Now, as for before, if you have observed the periodicity property clearly, we have established the fact that in the periodicity property, after a certain number of shifts in the signal will revert back to the original position. And basing on that concept, what we are doing is shifting along the circumference of a circle. So that is the reason for the circular shift. Now then, let us move on to some of the examples of circular shifting. Suppose if a 4-point signal x of n be equal to 1, 2, 3, 4, where 1 being the origin sample, then let us define x1 of n, which is shifted by a value of n minus 1. That means it is delayed by one sample. And it is written in angular bracket for circular shift like this manner. Angular bracket for the number of shifts subscripted by the number of length of the signal and enclosed in the first bracket. So let us represent this signal in a circular domain. So what we have done is we have taken a circle and divided in 4 equal parts. Why 4 equal parts? Because the length of the signal is 4. If it was something other than 4, say 6, we should have divided the circle into 6 equal parts, and if it is 8, we have divided into 8 parts. But since we are working with a 4-point signal, we have divided the circle into 4 equal parts. So now let us define the signal. If this is the first sample where this position is x of 0, x of 1, x of 2, and x of 3. Of course, you know that. So this being our initial position, x of 0, and moving in this direction, this is x of 1, this is x of 2, this is x of 3. Now the representation is completely up in your hand. You can start from any of these points. That means you can take the first sample from here, here, or here. I have taken it from here. And also you can move the signals in any of the order. So what I say is, if we go in the clockwise direction, I am saying the signal is delayed. And in the anti-clockwise direction, the signal will advance if shifted. The converse can be also assumed as per the user preference. So if this is the representation of the signal, that is x of n, then what we are doing in this case is shifting, that means delaying the signal by a value of 1. So what will be the, let us write this values First, x of 0 will value 1, x of 1 has a value of 2, x of 2 has 3, and x of 3 has a value of 4. So the signal when shifted previously this point was 1, this point was 2, this point was 3, and this point was 4. Of course, I am talking about the signal values. So this is 1, and this point it is 2, this point it is 3, and this point it is 4. Now once we shift the signal by a value of 1, and since I have assumed the delaying direction to be clockwise, so this sample will go to the next position. So the new signal value, this will be 1, this will be shifted in the clockwise direction, 2, and 3 will be shifted over here, and 4 will be shifted over here. So, but the position x of 0, that means x1 of 0 is over here, x2 of 0 over here, x3 of 0, and this is x4 of 0 will remain the same. The marking location must remain same. All we are doing is just shifting the values. So x1 of n will be equal to, the first position the value is 4, in the second position the value is 1, the third it is 3, and finally the fourth position the value is, the second position, the third position the value is 2, and the fourth position the value is 3. This being the origin, so this is our required circularly shifted values. Now let us suppose what is the case for, say, another signal x2 of n, where we circularly shift n by 2 samples. So what happens now is you can compare with either this one or this one. Say I am comparing it with this sample, with this signal. So let us draw the circle. So the initial value for this signal x of n, the x0th sample is 1, x1 will be 2, x2 over here will be 3, and x3 over here will be 4. So now what we are doing is shifting by a value of 2. That means the 1 over here will be shifted twice. So 1 will go here, that is the first shift we got over here. And if we are to shift twice, so 1 will go from here to here. So this is 1. Similarly 2 will go to here. 3 will go to here. And 4 will go to this position. So the marking place remaining same. This is x2 of 0. This is x2 of 1. This is x2 of 2. And this is x2 of 3. So we get the values for this signal to be 3, 4, 1, 2. So this is our required signal. Finally, let us see what is the case if we are to advance the signal. Say x3 of n is equal to, before going that, if you are to compare it with this signal x1 of n, what we need to do is just shift it once instead of twice, because we have shifted x1 of n once before. So shifting it twice will result in 3 times shifting, and that will be an error. So x3 of n, where x is shifted such that n plus 3, and we are to determine the value. So now, comparing it with our initial signal x of 0, let us observe. So these are our 4 equidistant points. So the value over here is 1, it is 2, it is 3, and this is 4. Now what we are doing is advancing the signal by 3 times. That means since we are delaying in this direction, in the clockwise direction, so it is quite obvious advancing the signal will result in moving the samples in the anti-clockwise direction. So the first sample 1 will be shifted thrice in the anti-clockwise direction. So 1 will go from this 1 shift, 2 shift, and this is 3 shift. This value will be 1. 2 will be shifted 3 times. So this is 1 shift, 2 shift, and the thrice shift. This will be the new value. 3 will be shifted thrice. This is 1 shift, 2nd shift, and the 3rd shift. This will be the value of 3. And 4 will go to 1 shift, 2 shift, and the 3 shift over here. So the newly resulted signal, this being x3 of 0, x3 of 1, x3 of 2, and x3 of 3. So this will be 3, 1. Okay, there seems to be an error. So let us see. Where will these both cannot be 3 at the same time. So there is a slip of pen. This value will be 4. So the signal is 4, 1, 2, 3. So now let us look at another example, x4 of n, such that x is time reversed. That is, x is reversed in the circular domain. So comparing it with the initial signal, let us draw the circle. This being our 4 equidistant point. So initially the value over here is 1, this is 2, this is 3, and this is 4. So in case of x of n, the signal is rotating in the clockwise direction, like this. This is 0, 1, 2, 3. But what essentially happens if we are to reverse the time? So since the signal was rotating in this direction, a time reversal means that the signal will change its position and start to rotate in the reverse direction. So earlier it was going in this direction. For time reversal, it will have to go in this order. So the first sample, it will be here and not change the position since this is the origin. the second value will come over here. So we are simply writing the value in the reverse order. That is what we are doing. So this is the first sample, which is value is 1. So this is 2, this is 3, and this is 4. So this is our resulted time reverse signal, which value will be 1, 4, 3, 2. This is our time reverse signal. So I hope you have understand what is circular shift, and we shall now study the properties regarding the circular shifting. Now, in this case, I have assumed the direction of the signal to be moving in a clockwise direction and the origin point to be the topmost point in the circle. But this is not always true, as I have said before. In the later examples, I might as well assume another point to be the origin and move in either of the direction, and hope you will understand the nature of shifting. Okay, then now let us move to the property, the next property, which is the time reversal property. Okay, now what the time reversal property essentially states is that if x of n has a DFT pair x of k, then the property states that the time reversed value, that is x of minus n capital N, will also result in a time reversed frequency domain signal. That means that if a signal is reversed in the time domain, the value will be such that the frequency domain signal is reversed after the transform. So we are going to prove this. So before doing so, we can write this signal as x of n minus n for simplicity. And this can be written as x of capital N minus k. Since in both the cases n and k will go from 0 to n minus 1. Now this can be verified using the previous example. I have said x of capital N minus n. So say if the value of n is 1, that is, we are working with x of 1, where the value of n is 1, and capital N in our case, since this is a 4-point signal, will be 4. So the result will be x of 4 minus 3 is 3. That means the time reverse signal will have the value at x of 3. So x of 3 in this case is 1, 2, 3. So, as I've seen, x of 1 was 2 in this position, and when time reversed, the value 2 is found over here at the third sample. So it is quite mathematically correct if we write the time reversed notation as this. So now moving on, let us go to the proof. Since x of k is given as n which goes from 0 to n minus 1, x of n e to the power minus j twice by nk over n. where obviously k will range from 0 to n minus 1. Then the DFT of x of capital N minus n will be equal to summation where n goes from 0 to n minus 1. The signal earlier it was x of n, now since it is x of n minus n, this will be x of capital N minus n e to the power minus j twice pi kn over n. The remainder of the signal will be same as before. So let us assume if any arbitrary variable m is equal to capital N minus small n, then n will be equal to capital N minus m. Now if n goes to 0, then capital N minus m will also be 0, since this is the value of n, and m will go to n. So if n is equal to 0, m will be capital N, and if n is equal to n minus 1, then n minus m will be equal to n minus 1, and m will be equal to 1. So changing the variables of this equation, we get summation, earlier it was n, now this will be m, which goes from capital N to 1, and x of m e to the power minus j twice by capital N minus m k over n, just replacing the value of small n over here. Now, as I have said earlier, in case of the DFT or DTFT, we can consider the sample from 0 to n minus 1, or we can consider it from 1 to n. The only condition being that we are working over n number of samples. So in the previous case we were working from 0 to n minus 1. Now we are working from n to 1. So following this condition, it is sufficient to write m which goes from n minus 1 to 0 will also be true. X of m e to the power minus j twice by capital N minus m k over n. Okay. Now then, as I have shown earlier in one of my earlier videos, a peculiar property of the summation operator is that if it is independent in nature, we can reverse the upper and lower limit, and it will not hamper or take any